Somewhere among the countless galaxies, the darkness harbors a mystery. What if the Milky Way is drifting in a vast cosmic void, an immense bubble of emptiness? What if this void distorts our understanding of the entire cosmos? Could this emptiness be the missing piece of a puzzle that has haunted astronomers for decades? Could it be the answer to the problem known as the Hubble tension? We're used to thinking that the universe is uniform, but modern research suggests our galaxy might lie inside a giant bubble roughly 2 billion light-years across. But first, it's probably worth starting with the core of the problem that has troubled physicists for years. There's a number called the Hubble constant. It's a value that tells us how fast the universe is expanding. In essence, it indicates how fast the galaxies are moving away from us to each megaparsec of distance, about 3.26 million light-years in miles per second. But there's a problem. Not everyone agrees on what that number is. When we measure the rate of expansion in the early universe using the cosmic microwave background, the afterglow of the Big Bang, and large-scale models like the baryon acoustic oscillations, we get a value of about 41.6 miles per second per megaparsec. However, when we measure expansion in the nearby universe using observations of Cepheid variable stars and Type 1a supernovae in relatively close galaxies, we consistently get a higher value, about 45.4 miles per second per megaparsec. That's an 8% difference in the rate of cosmic expansion. An 8% discrepancy might not sound like much, but in cosmology it's huge, well beyond any margin of error. In fact, this standoff between 41.6 and 45.4 has persisted and even intensified as our measurement methods have improved, reaching a high statistical significance of about 4 to 5 sigma, meaning it's extremely unlikely to be a fluke. This phenomenon was named the Hubble tension, often referred to as the most exciting crisis in cosmology because it challenges our standard model of the universe. Essentially, the universe today is expanding faster than we might expect based on the conditions of the early universe. And this raises big questions. Have we misunderstood how the universe evolved? Could unknown forces or new physics be at play? Scientists have thoroughly checked and double-checked these measurements. Could it have been an error? A series of meticulous cross-checks shows that the discrepancy really exists. In 2023, NASA's Hubble and James Webb telescopes teamed up to rule out subtle errors in the local distance ladder. James Webb's sharper infrared vision allowed astronomers to look at distant Cepheid stars previously measured by Hubble and eliminate concerns about blended starlight or calibration mistakes. As a result, Hubble's measurements were confirmed. No hidden systematic error was found to explain the discrepancy. As Nobel laureate Adam Rice said, "With measurement errors negated, what remains is the real and exciting possibility we have misunderstood the universe." So if it's not a mistake, then what could explain this faster than expected expansion? Many ideas involve new physics, perhaps a new type of dark energy in the early universe, unexpected particle physics, or other exotic tweaks to the lambda CDM model. But these solutions are often complicated and create new problems. Nevertheless, there's another intriguing possibility that does not require rewriting the laws of physics at all. What if the problem is not in the cosmos itself, but in our perspective? What if we live in a special region of the universe, a vast bubble of relatively empty space, which makes the expansion around us appear faster than average? That's the hypothesis we'll explore today: the Milky Way inside a massive cosmic void. Cosmic voids are exactly what they sound like: enormous regions of space that contain far fewer galaxies, gas, and dark matter than the cosmic average. If the large-scale structure of the universe resembles a cosmic web, then voids are the vast empty gaps in that web. They are like dark cosmic seas between the bright islands of galaxy clusters. Voids can be incredibly large. A great example is the Boötes void, a spherical region hundreds of millions of light years across, containing very few galaxies. However, these areas are not entirely empty. They do contain some matter, but much less than average. In cosmological models, voids form naturally. Gravity pulls matter into filament-like structures, drawing it out of the spaces between them. Over billions of years, the rich areas get richer, forming clusters and superclusters, while the gaps become more desolate, forming voids. Our cosmic neighborhood is no exception to this foam-like structure. In fact, astronomers have long suspected that the Milky Way is adjacent to a local void. Just beyond the boundaries of the local group of galaxies, there is a known region called the local void. Not to be confused with the larger structure we're focusing on now. This local void is a relatively small, underdense region stretching 30 to 150 million light-years by a rough estimate, first identified by Tully and Fisher in the 1980s. But beyond our immediate vicinity, at a much larger scale, evidence has emerged of something even bigger, an enormous underdense region encompassing us and many nearby galaxy groups, a supervoid of unprecedented scale. In 2013, astronomers Ryan Keenan, Amy Barger, and Lennox Cowie reported evidence that the local universe is underdense with a radius of 300 megaparsecs, which is about 1 billion light-years. By counting galaxies and measuring total light in the near-infrared spectrum, they found that galaxy density around us is lower than the cosmic average. Up to a redshift corresponding to roughly 1 billion light-years, galaxy density slowly increases. By the time you look beyond that distance, the universe's density is about 1.5 times higher than in our region. In honor of the people who discovered it, this massive underdense region was nicknamed the KBC void, sometimes referred to as the local hole. It is a giant void about 2 billion light-years across, one of the largest ever discovered, if it truly exists. Further studies have supported this picture. For instance, in 2014, Whitbourne and Shanks discovered a similar local hole using galaxy redshift surveys and peculiar velocities, suggesting that the local group is in a significant underdensity. A later study, conducted in 2017 by Chiang and colleagues, also found hints of local inhomogeneity using standard candles. All this data points toward the possibility that our cosmic neighborhood may lie within a giant void, rather than in an averaged-out uniform patch of the universe. To distinguish it from the smaller local void, scientists refer to it as the large local void or the KBC void. A void of this scale is a fascinating concept. It doesn't break cosmology. It is possible for the universe to have large structures. A void 1 to 2 billion light-years across pushes the limits of what's expected in the standard model, a rare fluctuation, but not impossible. If our galaxy is near the center of this void, it would be an interesting twist on the Copernican principle, the idea that we do not occupy a special place in the universe. Living in a giant cosmic bubble might seem like a coincidence, but if it's true, it could have deep implications for how we interpret astronomical observations. So, here's the question. If we're actually inside this enormous void, how does it affect us? How could it impact measurements such as the Hubble constant? The key lies in gravity and motion. In a significantly underdense region, gravity is weaker than in denser regions. Matter within the void, including galaxies, gas, and so on, feels a slight pull outward towards its walls with higher density. This causes a gravitational outflow, Galaxies near the interior of the void tend to move outward toward the edges where there's more mass. Imagine being atop of a small hill. Affected by gravity, objects naturally roll down toward the surrounding areas. Now imagine that from inside the void, we observe galaxies that lie outside it, in the denser outer universe. These galaxies are essentially downhill from us in terms of gravity. As light from these distant galaxies travels towards us, it climbs out of the void's gravitational well, while the galaxies themselves move outward. As a result, from our point of view, distant galaxies appear to be receding faster than they would otherwise. In other words, the expansion rate we measure locally is inflated. The void acts like a lens or bubble, adding a redshift component to the light from distant objects we observe. If the void is large and underdense enough, calculations show that it could increase the observed Hubble constant by about the same amount as the Hubble tension discrepancy. In essence, being inside a large void could make our expansion rate about 8% faster, turning a true global constant of 41.6 into a local apparent constant of 45.4, which matches the observed tension. This idea isn't just qualitative. Scientists have quantified it. In 2020, a team led by Moritz Hausbauer, Adrani Banik, and Pavel Krupa closely studied how a 20% underdense void with a radius of 300 megaparsecs, the KBC void, would affect cosmological observations. They found that a void of this size could indeed raise the local Hubble constant by about 5 to 8% due to gravitational redshift and the outflow effect, possibly resolving the tension. We should reiterate that this doesn't require any new physics. This solution relies on ordinary gravity from general relativity and a slightly inhomogeneous universe. It reminds us that the cosmological principle, the assumption of large-scale uniformity, is an approximation. A very good one at extremely large scales. But at a scale of a few hundred megaparsecs, there may be significant deviations. If we happen to live in one of those areas, we must take it into account. To make this more intuitive, imagine the universe as a loaf of raisin bread expanding in the oven, a common analogy for cosmic expansion. Normally, each raisin, a galaxy, sees other raisins moving away uniformly. But if our raisin happens to be where the dough is slightly less dense, like a large air bubble in the loaf, the neighboring raisins would be more sparse. Here, the dough plays the role of gravity. Around us, the dough is less dense, making it easier for surrounding raisins to drift apart. From inside the bubble, it would seem like the expansion is happening faster. This isn't a perfect metaphor, but it conveys the idea that our large-scale environment could distort our perception of the Hubble constant. It's an elegant idea, perhaps too elegant. Extraordinary claims require extraordinary evidence. Is there actually proof that this giant void exists, and it's affecting our measurements? As mentioned earlier, the first hints came from galaxy counts. But scientists have been searching for other, more precise ways to test this hypothesis. Arguably, the most striking evidence came in 2025. Adrani Banik from the University of Portsmouth and his colleague, Vasilios Kalazides, conducted a thorough test using 20 years' worth of baryon acoustic oscillation (BAO) data. BAOs are faint periodic ripples in the large-scale distribution of galaxies, essentially fossilized sound waves from the early universe imprinted into matter. They serve as a standard ruler about 1 billion light-years in length. Since the actual physical size of these ripples is known from early universe physics, astronomers can compare it to the apparent size in the sky at various distances to trace the history of expansion. Banik's idea was this: if we're in a void, BAO measurements at different redshifts should deviate from the standard homogeneous model in a specific way. So Banik and Kalazides completed 42 BAO measurements from various galaxy surveys over 2 decades including recent data from the Dark Energy Spectroscopic Instrument, which maps galaxies and quasars with high precision. Then they compared two scenarios, the void-free Planck lambda CDM cosmology and a model with a void as previously proposed in earlier works. The results were striking. In the void-free model, BAO observations at low redshifts began to systematically deviate from predictions, with distances inferred from BAO slightly off. But in the void model, these discrepancies largely disappeared. The data aligned significantly better in all respects. They quantified this as a reduction in BAO-related tension from about 3.3 sigma to just 1.2 sigma, essentially eliminating it. In other words, the void-based model was tens of thousands of times more likely given the BAO data than the standard homogeneous model. According to Banach, the Planck-based model without a void showed the worst fit in almost every case, whereas the void model outperformed it. These BAO results are perhaps the strongest evidence yet in favor of the void scenario. The fact that an independent cosmological probe, BAO, unrelated to supernovae or Cepheids, points to the same effect gives real weight to the idea that our local patch of the universe may not be average. Importantly, Banach's analysis was driven by the void hypothesis before he looked at the BAO data, and indeed, the BAO behavior systematically increases with decreasing redshift, just as the void model predicts. In science, such success and prediction is very compelling. The idea that we live in a giant void has nearly philosophical implications, but its major strength is that it doesn't break any known laws of physics. Instead of searching for a new form of dark energy or tweaking general relativity, this hypothesis simply suggests that maybe our observational challenges stem from an oversimplification, the assumption that we live in a perfectly average place. If the Milky Way resides in a region of unusually low density, then our measured expansion rate would be slightly overestimated. Once that's accounted for, the Hubble tension mostly disappears. The universe's overall expansion could still match the value inferred from early universe observations, meaning our standard cosmology remains intact. This explanation is pleasantly laconic, and unlike some more speculative solutions such as a new form of early dark energy that mysteriously appears and disappears, a void is something we know can exist in principle. It doesn't introduce new fundamental entities. It just suggests that we may have drawn the short straw, living in a particularly empty patch of cosmos. That said, this doesn't mean the case is closed. As of 2025, the void idea, while promising, has not yet gained broad consensus. The KBC void remains a hypothetical structure, though with growing evidence. One problem is that if the void is too large or too deep, it might contradict expectations of the standard model. It must strike a careful balance, just enough to fix the Hubble constant, but not so extreme that lambda CDM couldn't produce it. Some researchers have also published counter-arguments, for example by reanalyzing supernova data and claiming that once selection biases are handled, the evidence for huge local void diminishes. There's still ongoing vigorous debate regarding this issue. Upcoming research and observations will be key to finding answers. Projects like ESA's Euclid and NASA's Roman Space Telescope, both launching very soon, will map the large-scale structure and expansion history with unprecedented detail. Still, this hypothesis has undeniably shifted the conversation. If our local cosmic structure affects how we perceive the universe, it raises profound questions. How else might our unique vantage point distort our understanding of the cosmos? Are there other cosmological measurements being skewed by local structures we haven't yet accounted for? If we'd been in a denser region, Would we have discovered dark energy in 1998 in the same way? Or would the universe's acceleration have appeared different? Moreover, if the Hubble tension is resolved by a void, it highlights that to truly understand the universe, we must consider the context from which we measure it. On the other hand, if the future evidence rules out the void as the explanation for the Hubble tension, we'll have to pursue new theories, a prospect that is just as exciting. Either outcome will provide us with crucial information. Either the universe has fooled us with a colossal cosmic illusion, or we're on the brink of discovering entirely new physics that goes beyond our current understanding.